Hello everyone, I'm Yatharth, and on behalf of my team and colleagues, I am here to present our work on development and deployment of hybrid controller-based dual-axis solar tracker. So this paper presents the development and control of a photovoltaic dual-axis solar tracker system. The problem of energy harvesting has profound applications, and the dual-axis tracker is a well-established method of solar energy acquisition with proven contribution and improvements over traditional methods. The system constructed in this study caters to the application of renewable energy harvesting techniques to a mobile street vending cart solution. Therefore, with the advent of mobile technology and sophisticated electronics deployment, a versatile version with robust control strategy is desirable of the famous technology. The strategy of control deployed is that of a hybrid controller, which is a novel combination of astronomical equations based on open loop control and differential flatness based control over the tracking movements of the photovoltaic panel used. Finalized prototype was tested in overcast and sunny conditions to evaluate performance against a static solar energy photovoltaic harvesting system. The developed tracker uh, increase the energy acquisition by more than 25%. Now, moving on to the experimental setup, first from mechanical perspective, a robust frame design was required to execute actuation commands and support the panels in their motion and was designed accordingly. As we were aiming for maximum solar energy acquisition, we targeted for a time duration of 9 a.m. to 3 p.m. And the maximum angles required for this time was found out to be 65 degrees to 112 degrees about the transverse axis and 75 degrees to 115 degrees about the longitudinal axis of the solar panel. This linear actuator positioning was assumed to have the bottom pivot passing through the center line of the pin between panel and frame support at point B and at point O, as shown in figure 1. The horizontal and vertical dimensions to position the linear actuator are defined as x and y respectively. The stroke length of the longitudinal actuator was kept to be around 20 centimeter, and that of transverse actuator was about 15 centimeter. The solar tracker was fabricated using aluminium, and the total weight of tracker setup was around 16 kgs. Now, moving on to the experimental setup from electrical and systems perspective. In the proposed system, LDR sensors convert the light intensity into equivalent resistance. This output is supplied to the microcontroller, which identifies highest intensity light direction based on program fed to it. Then microcontroller using customized algorithm will operate the system of varied stroke length of linear actuators to rotate the 125-watt solar panel around two mutually perpendicular axes to capture the greatest amount of sunlight. The system model was obtained by linearly regressing over experimentally captured data to specifically determine the coefficients in our model equations. Now, regarding the tracking system of our setup, optimization requirements for speed and accuracy of tracker orientation with respect to solar axis demands for a precise control methodology. This problem of precise tracking has been approached here with a hybrid model of controller, that is astronomical method and sensor-based feedback method. The system operates using two electromagnetic actuators fixed in complementary fashion, offering 2 degrees of freedom. And the input data to the system is from first magnetometer and RTC sensors for approximate astronomical alignment, and LDR sensor data for real-time final adjustments of the solar panel. The overall data sensing and algorithms deployed for the tracker can be represented in the following figure, where we start with gaining sensor inputs from RTC, magnetometer, and LDR. RTC and magnetometer data is used to calculate our solar orientation angles using the empirical astronomical formula, which is used to achieve course orientation of our panel. And LDR sensor data is used to achieve finer orientation of a panel using the sensor-based closed-loop control algorithm. Now, talking specifically about the astronomical tracking system, achieving coarse panel orientation of the solar panel with respect to solar axis is done using this method of declination clock manipulation. It is based on the principle of pseudo azimuthal system of determining the solar orientation using empirical equations and extracting its components over two axes. The two angles obtained from this procedure, declination and clock angles, are used on longitudinal and transverse actuators as they are shown in the corresponding figures. Now, talking about our closed loop flatness based controller, as we know, our differential flat system is the one in which an output, flat or output h here, can be devised as a function of the system's state x and inputs u and their derivatives. A flatness based generalization of any system is established by exploiting the equivalence of initial and final systems. This results in characterization of the system in terms of flat outputs as non-differentially algebraic over flat outputs differential field. A linear system such as the one under consideration can be considered as a flat system only when they're controllable. The flatness-based approach enables us to devise a state x and input u of the system in terms of flat outputs and its derivatives. Now, talking about flat outputs, a linear system's input and state variables has been expressed as follows, where x is equal to p into y and u is equal to q into y, where p and q are polynomials which follow the matrix output characterization treatment and help in expressing the system variables in terms of the flat output. This enables further proceeding in flatness-based controller design. For the dual-axis solar tracker system in this study, we have the flat output based system model for the transverse and longitudinal actuator subsystems as depicted in the equation where x and u state and input respectively. Now, the next step is that of trajectory generation. The trajectory-based motion control has its advantages in better motion tracking and lesser power demand. This particular derivation follows the Newton's interpolation applied to the system's outputs at initial time and final time, providing a robust trajectory reference over the period of operation. Taking y1 and y2 as reference trajectories or outputs, the system's control can be thus implemented using the following equations, where the gains are calculated using dominant pole method to form closed loop dynamics. Now, talking about the results we obtained from our experiments, to evaluate the performance of dual-axis solar tracking system, as shown in figure, we have compared the power generated from a solar panel when attached to the tracking system with a static solar panel, which is devoid of any orientation mechanism. The power was measured by observing open circuit voltage and short circuit current of the panel during the certain time interval of operation. The measurements here are done with the help of a multimeter. The results of the experimentation are shown in figure, which shows the performance of the system when a PID controller is used to process error generated from data received from LDRs and magnetometer. And here the figure shows the performance of a flat controller based algorithm. The performance of the system is also tracked in overcast conditions to compare it with optimal sunny conditions. The tracker system is able to increase the power generated by a factor of around 20%. We have compared the results for multiple weather conditions as seen here, and the proposed tracker system works well for both sunny and overcast conditions, thus showing the robust nature of our system. Now, to summarize our results and to lay what we did here, the developed solar dual-axis solar tracker system in this study operates in tandem with the requirements, and it works well for both sunny as well as overcast conditions. The fast-acting control mechanism acts in accordance to the requirements in a mobile setting, and the average energy increase in performance, which is the figure to look at, is shown in table one, where as we can see In overcast conditions, the flat controller based hybrid controller increases the power generation by over 21%, and in sunny conditions, it increases by over 25%. And these are the references which help us throughout. Um, that's it from my side. Thank you all for your patience. I hope this was enriching as well as and helpful for the causes. Thank you.